All right, so indeed, I'm going to talk about formally separating between strategic and non-strategic behavior. And fear not, I will tell you what on earth I mean by that first. I'm James Wright. I'm from the Alberta Machine Intelligence Institute at the University of Alberta, and I'm going to be presenting joint work, or this work that I'm presenting is joint with Kevin Leyton-Brown at UBC. So I want to open by focusing on what is perhaps the foundational question in game theory, right? Which is, how should a rational agent act when there's other agents around? And I argue that the answer is they should act strategically. And what do I mean by that? I mean they should do a couple of things. So first, they should be modeling the other agents. They should have some kind of probabilistic beliefs about the actions of the other agents. And then once they have those beliefs, because we're constraining them to be rational, they pretty much just have to best respond to them. They have to take the expected utility of every action with respect to those beliefs, and they have to pick the thing that maximizes their utility. So another way of saying this is when we say perfectly rational in game theoretic settings, what we really mean is the agent has to behave optimally. And so when there's other agents around, you don't have any choice but to behave in this way, where you think about the other agents and respond to what you think they're going to do. If you do anything else, if you behave in any way that isn't strategic in this sense, you're behaving suboptimally. And so the question of, when you're thinking just about rational agents, the question of what kind of behavior is strategic and what kind of behavior isn't strategic doesn't really arise, because all perfectly rational agents must simultaneously be perfectly strategic when they're in one of these interactive environments. But it gets a little bit more complicated when you start thinking about boundedly rational agents. So a boundedly rational agent is one that isn't crazy, right? They're not nuts. They're behaving in some way that is somehow sensible. However, they're not magic either. They're not perfectly optimal in every possible situation. Okay? And so once you're in this setting, you can ask yourself, do they always have to behave strategically? And really, what do I even mean by that? So we'll take a first informal stab now, and then we're going to zero in a little bit more on this intuition later in the talk. So the first thing that a boundedly rational agent might need to do if it's behaving strategically, I'm going to say that they must be modeling the other agents. But we're not going to restrict them now to be using probabilistic beliefs, and we're not going to restrict them to be magically correct, as we often do with perfectly rational agents. And second of all, they must somehow be aware of what's good for them. So they've got to somehow be changing their behavior in response to their incentives. But again, this doesn't necessarily have to be exact maximization, right? This could be some other thing that's related to that or approximates that or something like that. So once you have these smart but not perfect agents, the distinction between behaving strategically and not behaving strategically or behaving non-strategically, it becomes meaningful. This becomes a question that you can meaningfully ask. So great, the question is meaningful, but is it interesting, right? Like, we can ask it, but that doesn't necessarily mean we care. And so now I want to argue that you should care, okay? So what really caused this to come up for us was our work in behavioral game theory. And one of the most prevalent models in behavioral game theory is the family of iterative models. So I'm going to describe to you a member of that family called the level K model, just because it's the easiest to go through. So in this model, you divide the agents up. They all have a bunch of levels. Okay, so every agent has some integer level associated with them. So we start with the level 0 agents, and they behave uniformly at random. They're completely crazy. The level 1 agents think everybody else in the world is level 0, and they best respond to those guys. Okay? The level 2 agents think that everybody else in the world is level 1, and so they best respond to those guys. So they think about, what would a level 0 agent do? Then they think, well, what would a level 1 agent do in response to that? And then they think, aha, I'm going to best respond to that. And you can keep going as far as you want, although empirically it turns out people don't go very far at all. So clearly, the level 0 agents in this kind of a model are non-strategic. They're not really aware of their own incentives. They're not thinking about the other agents at all, right? But the higher level agents are strategic in a fairly precise sense, because they are forming, in fact, a probabilistic model of what the other agents are going to do. And they are, in fact, best responding to that. Although there's also variants where they'll quantily respond or sort of noisily best respond to that. And so in this specific setting, it's quite clear that we have a very sharp distinction between the strategic agents and the non-strategic agents. But it's a little bit limited because it's not very plausible in a lot of settings that anybody in the universe would behave uniformly at random. That the early work in level K models actually works in situations where it isn't nuts to think that people would behave uniformly. So I don't intend this as a slam. But there are other settings where different kinds of level 0 behavior might make a lot more sense. And indeed, there's work in those areas. And so when you're working in those areas, you often argue heuristically for some other rule for your level 0 agents. You say, this is the non-strategic rule that the level 0 agents are going to do, and then I'll build out my level 1, level 2 hierarchy on top of that. And so, for instance, you might say that agents are going to go for the biggest number in something like Traveler's Dilemma. You might say that they're going to truthfully report their values in something like an auction setting. And you just kind of heuristically or intuitively argue that, like, they're not really thinking strategically when they do this. This is just what they do. So here's a list of some of the things you could imagine a level 0 agent doing. And I want to show that this kind of intuitive hand-wavy argument starts to break down pretty quick. Okay? So first of all, uniform randomization, I don't think there's really much argument. That's a non-strategic behavior. I think you can make a pretty strong behavior that maximizing your worst case or maximizing your best case are both also pretty non-strategic, because you can do both of those things just by looking at your own utilities. If I'm not looking at the other guy's utilities at all, it's pretty hard to argue that I'm forming a very sensible model of what he's doing. But then there's other things that you could also do. You could say, maybe I'm going to be somehow altruistic, and I'm going to start aiming toward the outcome that has the best total payoff for everyone. Or maybe I'm going to aim for the outcome that is minimally unfair in some sense. So there's a small difference in utilities among people. I've got a star there because my mathy definition here is just for 2 agents. It's a little bit of a pain to extend that to multiple agents, but it's not too hard. And you could imagine, well, actually, maybe level 0 is just Nash equilibrium. Maybe I assume that everybody's behaving in some sort of equilibrium. Okay, I'm going to claim to you that it's pretty obvious that Nash equilibrium is not a great level 0 model, because to figure out what the Nash equilibrium is, typically you're going to want to have to think about everybody else's incentives. It's about as strategic as you can get. This is what rational agents do. But there's a sort of mushy middle ground in the middle, where, if you look at total payoffs or you look at minimum unfairness, on the one hand, I'm not really giving the other agents credit for being agents. I'm not imagining that they're going to be doing something to maximize their own utility. I'm just kind of picking an outcome that I like and aiming towards it. But on the other hand, I do still have to think about other agents' utilities. So this kind of really obvious argument that I was making for the max min and max max cases is not going to go through. And then, in fact, it turns out to be even more complicated than that, because max max isn't necessarily non-strategic if you don't have a formal model. Because one argument you could make for max max is you could say, well, actually, what's going on here is the agents have formed this belief that it just so happens that they think the other agent is going to play the action such that if I best respond with my max max action, I'll get my max utility. They somehow have this belief that the other agent is playing in a way that's advantageous to them. And so you can actually model max max as best responding to some sort of probabilistic beliefs that they might have. So in this talk, what we're going to talk about is we're going to give a formal definition of strategic behavior that's not equivalent to this sort of perfect rationality that I described. And then we're going to go a little bit further than that. We're going to give a constructive characterization. So I'm going to give you a class of functions that are guaranteed always to be non-strategic, and that in some sense cover the space of non-strategic functions that are sensible in a certain way. Okay. So to do that, I need to define a behavioral model for you. So a function, I'm going to say a behavioral model is just a function that takes in a gain, and it gives a probability distribution for a single agent's actions. So this is something that you could imagine an agent running in order to figure out what they're going to do. So it's not quite the same as a mixed strategy, because a mixed strategy is associated with just a single gain. And it's also a little bit different from a solution concept, because it's giving you a single agent's behavior, and it's giving you a single distribution over what they're going to do, rather than some set of things that's acceptable. And so what we're up to here is we want to identify the models, right? So we want to have some condition that applies to these mathematical models that tells us which ones are non-strategic. So recall that we think that a model is strategic if it satisfies 2 properties. It has to model the other agents, and it has to respond to its own incentives. So we're going to give some formal properties that capture these notions. And so the formal properties are called other responsiveness and dominance responsiveness. So I'm going to say the behavioral model is other responsive if there's any pair of games anywhere at all, such that when I apply my model to them, I do different things, And the model and the games themselves only differ in the payoffs of some other agent. Okay, so what this is saying is that if I ever change my behavior just because some other agent's payoffs have changed and not mine, then I'm responding to the other agent's payoffs. Okay? So notice this is super duper weak. I'm not committing to any particular way of modeling what the agents are going to do. I'm not grounding this out in how the other agents are going to behave. I'm literally just saying if it's possible to change my behavior at all just by changing what the other agents are going to get, I must be thinking about them somehow. And we've got a similarly weak notion for responding to your own incentives. So we're going to say that a behavioral model is dominance responsive if it's the case that if I pick two games where there's some action that is strictly dominant in one game and strictly dominated in the other, then the model is not going to behave identically. I'm somehow going to change my behavior. And so again, this is saying that if I've just changed my own payoffs in some way, this is kind of like the twin to other responsiveness. This is saying if my own payoffs change in some very weak way, some very gross, strong way, I'm going to change my behavior at least somehow. And so notice that again, this is super duper weak. I'm not requiring that I'm going to play the dominant action more when it's dominant than when it's dominated. I'm just requiring that something is going to change. Okay? I'm also not requiring that the games have similar payoffs in any way. I can change stuff in kind of an arbitrary way. So now we can make our formal definition of what strategic means. So I'm going to say that a behavioral model is strategic if it's both other responsive and dominance responsive. This is a very weak notion, right? Both of these notions are weak. You stick them together, you still have something pretty weak. Why did I do that? We made this weak notion because what we're really up to here is we want a class that's going to capture things that are unambiguously non-strategic. So I'm going to say, here's a class of things that don't even satisfy this extremely minimal notion of strategicness. So they must be very non-strategic. So we can do a little sanity check. And so the first couple of theorems are unsurprising kind of by construction, right? It turns out that quantal response equilibrium, Nash equilibrium, and correlated equilibrium are all strategic behavioral models by this measure. I think we'd be in trouble if they weren't. I think we would have some serious intuition problems. And in the behavioral game theory world, it also, or I guess the iterative models world, all of the level K cognitive hierarchy and quantal cognitive hierarchy models are also strategic behavioral models for the agents of at least level 2. Okay, so what we're going to say is the level 0 agents are non-strategic. Good, that's what we want. The higher level agents are strategic. Good, that's what we want. What's going on with the level 1 agents is going to depend on how rich the level 0 strategy is, right? If the level 0 strategies are behaving in a completely crazy way, then I actually don't need to think about their payoffs at all to figure out how they're going to work. So think about the uniform randomization case, for instance. I don't need to know what their payoffs even are. The proofs follow for the proof of the second one follows pretty straightforward from the first one. The proof of the first one is annoyingly difficult. And we have to introduce this whole extra wheel called self-responsiveness to make it happen. Thank you. Okay, so we've got everything in place now. We've got a formal definition of strategic, and we have a mathematical sense in which we can prove that something is or is not strategic. And so now I'm going to give you the constructive class. This is going to be our candidate model for what is it that must be true of a model that's non-strategic. So recall, if you're strategically reasoning, you need to be accounting for a couple of things. You first need to be accounting for your own payoffs, otherwise you can't be dominance responsive. And you also need to account for others' payoffs. You need to think about those in order to be other responsive. So every time you think about an outcome, every time you think about what happens if we all did a certain thing, you have to think about it from multiple viewpoints in some sense. And so our candidate class of non-strategic models are models basically that don't do that. Okay, we call these elementary models. And the idea behind an elementary model is you score every outcome using just one number. And then you make your decisions based just on that single number for every outcome. Now, real analysis is annoying sometimes. There's this thing called dimension smuggling where I can encode arbitrarily many real numbers into one real number. Please don't do that is something we have to do a little work to make happen. And so we're going to define this thing called no smuggling. So we're going to say that a function is dictatorial if its output is completely determined by a single input. Okay, so what I mean by that is if I take a vector of m, but only one of those, only one element of the vector matters to my output, I'm going to say that the function is dictatorial. So it's kind of like in social choice. And then we're going to say a function is non-smuggling or no smuggling if either it's dictatorial or if it turns out for every single element of input, or sorry, for every single dimension of input, every single index, there exists a pair of vectors that differ in that input, but the function gives the same answer. Okay, so I can fiddle around with the other dimensions to make the output be the same. And it turns out that if you didn't set up your function specifically for smuggling dimensions, it almost surely satisfies no smuggling. In particular, linear functions do. In particular, any linear function. Sorry, I keep saying linear. Any continuous function is going to satisfy no smuggling. So this is, again, relatively weak. OK, so that's the sort of dotting of I's and crossing of T's out of the way. So what do we mean really by elementary? We're going to say that a model is elementary if it can be represented in the following way. You give me a game. And what I'm going to do is I'm going to create this potential matrix big phi. And I'm going to do that by applying little phi to every single element, to every single outcome of the game. Okay? And no phi, and little phi has to satisfy no smuggling. Once I've got this phi, I'm just going to run it through some arbitrary function called h. And that's going to give me my predicted behavior. So just to quickly run through how that works, let's take our arbitrary two-player game G here. What do? We're going to apply this same little phi to every action profile. So that's going to give us this new matrix that we'll call big phi. And then we send that big phi to our arbitrary function h, and it's going to give us some distribution over the actions of G, or over the actions of one of the players of G, I should say. That's how these things run. So now we can check on our original candidate level 0 actions that we were unsure about. And we can ask ourselves, do these satisfy the elementary behavioral model definition? So as we already remarked, max and max min, they only depend on the utility for a single agent. So I can set my little phi to just say, I'm going to look at just the input of that agent, just the utility of that agent, and skip everything else. We know that little phi satisfies no smuggling because it's dictatorial. And so then I can just use the h on those inputs and calculate my distribution as desired. So great, those are indeed elementary functions. Similarly, if you want to say I want to play toward the outcome with the maximum total payoffs, then I can just set my little phi to be the sum of the utilities. Okay, that's continuous, and so it satisfies no smuggling. And then again, we can use h to operate on those values. And you can make a similar argument for minimizing unfairness. So near the end of my talk, I can now tell you the main result of the paper, which is simply that no elementary behavioral model is strategic. The proof is super fun. I promise it doesn't take long. So suppose that, in fact, I have this model, which is elementary, and in fact, the potential function is dictatorial. Then it turns out that obviously can't be other responsive, so we have a contradiction. Otherwise, I must be able to come up with two vectors of utilities such that one of the vectors dominates one of the vectors is bigger than the other for player I, let's say. So then I make a game. I make a game where player I has a dominant strategy. I make a dominant strategy in G1, which is opposite from the dominant strategy in G2. But all of the outcomes are these x's and y's that our function can't distinguish. So the first action is dominant in one, and the second is dominant in the other. So dominance responsiveness says they have to be different. But they can't be, because they both have the same big phi. And so we get a contradiction. OK, finally, you might wonder, can I aggregate these things? Can I use these elementary models as a building block to make another elementary model? It turns out you can't. It turns out finite aggregations of elementary behavioral models are not necessarily elementary. And we can just prove that with a counterexample. But the good news is they're also non-strategic. So if I aggregate a bunch of elementary behavioral models, it's going to turn out that I have something that may not be elementary, but it's still non-strategic. So in fact, this is a still larger class of non-strategic functions that are easy to check for. So what have we done here? We've introduced the first formal separation between strategic and non-strategic behavior, which allows us to do a couple of things. First of all, it allows us to be a lot happier with our use of iterative models because we can check whether we've picked an acceptable level 0 specification. But also, when we want to take a machine learning approach to this, this is going to allow us to optimize over a precisely defined class of non-strategic behaviors. So we'll be able to tell if we've been exhaustive or not, or if we haven't, we don't have to worry that we haven't made a rich enough specification when we're trying to do machine learning in this kind of area. Okay, so that's the talk. I will just very quickly remind you what an elementary model is. The basic intuition is you take the payoff of vectors, sorry, the vector of payoffs, and you reduce it to a single number, and then you do whatever. Okay, and the key is just you have to reduce it to a single number in this non-smuggling way. Thanks very much.